Hello all. In this video, we are going to talk about inline functions and calculating the runtime in C++. So in order to calculate runtime, we need the library chrono, and we need to use the namespace under standard of chrono. Now here there is some explanations for you if you want to read over that, which I got it from Gigs for Gigs. This is a very good website on C++ programming and many other topics. I really benefited a lot from this website, and I mentioned it as one of my references. And here it mentioned that when you define an inline function, if the function, what it does, it's very brief and fast and short. If you define a function in line, then it can reduce the runtime of your code. Now, inline function is basically what it is a request from the compiler. You're asking the compiler to deal with it as an inline function, not a command that the compiler has to basically follow. In some cases, the compiler will reject or ignore your request for inlining, and that is when the operation of that inline function is time-consuming. Like it has loops, it has some static variables, it has recursion in it, it returns types other than void, and the return statement does not exist in the function body, and it has switch or go-to statements. In those cases, it might be ignored. The way to define an inline function is using keyword inline. Everything else is the same. So here, both of my functions are returning the cubic value of an integer number, but one of them is a normal function without inline, the other one is an inline function. And in this case, actually, the compiler does not ignore my request, although my function is not void and it is returning something, right? So in this case, still I checked it, and seems like the inline function is much faster than the non-inline function. So it's not like if you have any of these necessarily it will be ignored, but it might. But loops typically they might. So it has explanation on what it does for a regular function and for an inline function that makes basically your inline function basically run faster. So, and I can read it for you. I would rather read it instead of me trying to rephrase it, because I think the explanation is relatively good. So it says when the inline function is called, the whole code of the function gets inserted at the point of function call, and the substitution is performed by compiler at the compile time. But for a regular function, when you want to execute that, okay, the CPU first stores the memory address of the instruction following the function call, copies the arguments of the function on the stack, and then finally transfers the control to the specified function. So before the compiler passes the control to your function, it does some extra stuff, handling memories, copying the arguments, and so on. And that is causing your regular functions runtime to be a little bit more than an inline function that is going to be basically running in one step instead of several steps. Okay? So that's what makes an inline function in general faster, and as I said, the way to go about it is using the keyword inline. So here I also have basically the measurement of the runtime, and as I said, for that you need the chrono library, and you need to use the standard chrono namespace. So the way you measure the runtime is like this. Here I have some basically value, right, which is the return value of these functions for the number 30. So I'm going to pass 30 to both of these functions and ask them to raise it to the power 3, right? So it's going to be 27,000 basically. And I'm not going to do that operation one time. I'm going to do it 100,000 times using each function, because I want a significant amount of runtime, right? Because if you just call each one of these functions one time, it's so small, even in microseconds, that you cannot see it. Okay? So you perform that calling function in a loop for 100,000 times, so you see a reasonable number in microseconds so you can compare. So what I do is, first I get the time of the computer right now using high_resolution_clock now. So I get the current time now using the high resolution clock. And I assign it to the variable start, or start time. The type of this variable, I call it auto. I let the compiler decide what kind of variable is a start time. I perform the exact same thing after my for loop is done, and again I call the now function, and this time I call it the stop time, and again type auto. And then the duration is going to be stop minus what? Start, but I cast it to what? To microseconds. So I say duration cast, the stop minus the start, converted into microseconds. Because necessarily the times that you have a start and stop are not in microseconds. They could be some counts. Okay, so here I'm converting them into microseconds. And so this duration now, I'm going to show it. And I'm not going to show it just by calling duration. I say duration.count. So if you want to see the amount of microseconds for the runtime, you have to say duration.count. And I repeat the exact same procedure, but this time using the regular function cube1. So I do it with cube, which is inline, and then I do it with cube1. I get the duration for both of them, and I'm going to show it to you. And if we do that, you see that the runtime for the inline function is a little bit less than 3,000 microseconds, while for the regular function is 5,000 microseconds, right? So it's like more than 60–70% extra runtime. Okay, so I guess this hopefully this video was useful to you, defining inline functions and getting the runtime, right? In MATLAB, all you do is tick and talk. In here, it's a little bit more involved, right? There is a little bit more casting and so on, but the idea is the same. You get a start time, you get a stop time after the code, and then you show that number. Over there, you do it with tick and talk. So hopefully this video was useful to you. I will see you in the next lecture.